Okay, peoples. This was the example that we ended with in the last video, and I mentioned these little bitty tiny peaks right here to the side, and we said these were really isotope peaks. We don't really pay attention to those. They're going to happen. All right, well, I want to kind of follow up on that topic before we do any more examples. And I just kind of want to maybe give you an idea of how often these isotope peaks show up and maybe what we can use them for, because they are important, right? So this little bitty tiny peak right there is representative of 87. That 87 peak can give me some information about the molecule, believe it or not. It just requires a little bit of calculation. That's all it does. As long as I have enough information at my disposal. Now, what do I mean by that? 86. Well, 86 gives me an idea of the fragment. That is basically the whole thing, right? And I could just sit down and write enough carbons and enough hydrogens in order to get to 86. But maybe I don't want to go through all of that trouble, and maybe I want a shortcut. That 87 is going to provide me a shortcut. So, what I'll do is that I'll clean off this slide, and we've talked about carbon 12. And we said this is close to 100% of the time. Not every time we're going to get a carbon 12. Sometimes we get a carbon 13. And we said that this is about 1% of the time, give or take a little bit. So every now and then, we're going to get a molecular peak plus 1. So if the molecule weighs 72, we could get the presence of a fat carbon, an isotope, and that will give me a 73 on the spectrum. And some people will think that's the M peak because that's the furthest one that they see on the right-hand side, and it's not. That is simply due to the fat little carbon that came along this time, and that doesn't mean anything. Just 1% of the time, it's going to be super little. So we'll see a peak at 72, and I'm just going to enlarge this up, and then right beside of that, we'll see a peak at 73. But it's going to be super tiny compared to the other one. This is known as the M+1 peak. It's the typical formula weight of the whole molecule. And 1% of the time, we get a fat carbon that weighs 1 extra. Carbon 12 to carbon 13, 1 extra. And we see that M+1 show up on the mass spec. It's a natural isotope. It's going to happen. You can't do anything about it. You can't change it. You can't make that thing disappear because it's present. Accept it. It accepts you. But we can use that to our advantage. And what we can do is that we can create an equation. We can take the percentage of the M+1 peak and we can divide it by 0.011 times the percentage of the M peak. And if we do that, we are able to get the number of carbons in the molecule. That's all we got to do, people. These are the numbers straight from the mass spectral data system. That prints off on the report. It's going to be right there in the table. No big deal. It's going to give them to me. I take those percentages and I divide them. However, I've got to remember I have to multiply that bottom number by 0.011. Why 0.011? Because carbon 13 shows up about 1.1% of the time. And 1.1% is 0.011. All right, so that's where that multiplier comes into play. So that's my calculation. The problem is that this only works with hydrocarbons. Hydrocarbons basically mean just carbon and hydrogen only. Oxygen cannot be in existence. Nitrogen cannot be there. Sulfur cannot be there. Any of those normal atoms that are involved in an organic molecule cannot be present here. It has to be hydrocarbon only for this thing to work, and that is it. So I want to show you an example problem. I'm going to show you how easy actually this thing is going to be. So here's an example, and it says the mass spectrum of an unknown compound has a molecular ion peak with an abundance of 43.27, and it has an M+1 peak with a relative abundance of 3.81. How many carbons are in the compound? Now, notice it didn't give me structure. It doesn't have to. Notice it didn't even tell me what the M peaks were. It didn't give me the total weights of the M peak or the M+1 peak. It just gave me the abundance of them. That's the only thing that it did. How tall were the peaks? That's all that it did. So here's the graph. I get a random M peak that's going to be right here, and the height of it, if we go over to the y-axis, is going to be 43.27. And then we're going to have a little peak right beside of that one. And if I go over to the y-axis, the abundance of that one is going to be 3.81. That's where those numbers are coming from. It has nothing to do with the molecule. It has nothing to do with the fragment. It has nothing to do with the weights. We're only looking at the height. That is it. And based on that, I can get an idea of how many carbons are in this compound. Simple as that. So what I do from the previous equation, number of carbons equals, well, I take the percentage of my M+1, and then I divide that by 0.011 times the percentage of the M peak. That is what that equation was, right? There we go. Percentage of M+1 divided by my percentage of the M times 0.011. So I'll set this equation up. The percentage of the M+1 is 43.27. So 43.27 goes there. Notice I didn't even change it. Don't change it to decimal, because this says the percentage of. It's giving me percentage. It's right there. There's no need to change the number. That's what it wants. Divided by, no, sorry. I'm going to erase that, put it in the wrong spot. 43.27 is the abundance of the M peak. Has a molecular ion peak of 43.27. That goes down here at the very bottom. 43.27 times 0.011. And then it says it has an M+1 peak with an abundance of 3.81. So 3.81 goes up here at the very top. So I'm going to bring out my calculator, and I'm going to simplify that number one at a time, just so we can take baby steps here. 43.27 times 0.011. And I get 0.4759. All right, so 3.81 divided by 0.478. I can't remember what that was. 89? No, 47597. So 597. All right. Then I'm going to take 3.81 divided by 0.47597. I hit enter, and that gives me 8.00. Folks, there you go. That's how many carbons are present in this molecule I injected on the mass spectrum or spectrometer. 8 carbons. Now, I'm kind of hand-tied here. I can tell you it's 8 carbons, but I can't tell you anything else. I can say 8 carbons are present in this hydrocarbon, but it's got to be hydrocarbon or this thing's not going to work the way that I've wrote it here. 8 carbons are present. I just don't know how they're hooked up. 8 carbons are present, but I don't know if they're a straight chain or if they're hanging off of a main chain or if they're forming a ring. I have no clue. But I know there's at least 8 carbons in total. More than that, though, if this is a hydrocarbon, that means only carbon and hydrogen are in existence. I can say 8 carbons. Well, how many hydrogens are there? Can't really tell you that either. Are there double bonds? Are there triple bonds involved? That changes the hydrogen amount. Is it in a ring? Is it in a straight chain? That changes the hydrogen amount as well. So I really can't go the next step and even tell you hydrogen content. I can only tell you the number of carbons, and that is it. But it's an equation. It helps us get another piece of the puzzle. It helps us to maybe narrow down some of the choices that are there. And this is one of the powerful things about the isotope peaks that I will see in a mass spectrum. Okay, with that said, this is called the M+1 peak, right? I could see a little bitty peak beside of that one. Where's that coming from? We call that an M+2 peak. Now, carbon typically is carbon-12 or carbon-13. If carbon-13 shows up 1% of the time, it's very unlikely that 2 carbon-13s would be involved in the molecule. The chances are slim to none. But there are atoms that have M+2s, which means the isotope that we're looking at, maybe it starts off at 12, but when they're fat, they're double fat. They'll come to us maybe as in 14s instead of 12s. All right, well, that was in terms of carbon. But there's other atoms out there that do have a tendency to create an extra fat one when they happen, and we call that an M+2. Well, what are these choices? Well, you see, there's a couple of different ones here. However, the most common M+2 peak that we see is happening with oxygen. Oxygen has a 16 weight on the periodic table, but oxygen can also come to a superfat, which will be O18. So if oxygen is involved in a molecule that gets shot on a mass spectrometer, we do have a tendency to find a fat little oxygen on it, and we would see a signal at M+2, meaning that if the molecule did weigh 72 when you did a formula weight calculation, we could see a positive signal at 74. And that 74 line is coming from the fact that this thing has maybe an oxygen involved. We could see a 73 as well, especially if we have a fat little carbon, and no one says that that can't exist. And if the molecule's got a fat little carbon and a fat little oxygen, then we can see that 72, add one more to it to get a 73, add 2 more to that to get a 74 and a 75. And we can see a positive signal at 75 because of it. But these things are going to be super, super tiny. But that's why you're seeing them. That's why we tell you to ignore them. And that's why those positive signals exist. It is a combination of all of these people. So M+2 peaks are going to be common. It typically comes from oxygen if it's there. But that's not the only one that can bring an M+2 peak. We'll look at that in just a second. An M+1 peak is always going to be found because everything typically has carbon in it, and that typically always will show an M+1 when that happens. All right, well, what are some other isotopes that I need to worry about? Here they are. You asked for it, and I gave it. All right, so up here at the top is my carbon-12 and my carbon-13. This is going to be an M+1 peak. It weighs 1 extra. Here's hydrogen. Hydrogen-1 and hydrogen-2. We call this deuterium. Pretty important. That was UV vis. Old light bulbs used to be made of deuterium till they changed them up on us. This is also an M+1 peak. But look at this. 0.01% of the time. Give me a break. We're not even going to worry with it. Compare that to carbon at 1% of the time. Well, we're going to see that line on the spectrum. But if this deuterium shows up 0.01, we're not even going to see the line. It's going to be so small. So this, we just kind of pretend like it doesn't even contribute to the M+1 peak because the percentages they're just not there. Nitrogen 14 and nitrogen 15. Well, nitrogen 15's 0.36% of the time. So that is an M+1 peak, 14 to 15, right? But this percentage is kind of small. We don't really contribute that M+1 peak on the mass spectrum to the nitrogen. Nitrogen will be in compounds, not as much as carbon is. The percentages it's not as high as carbon. So again, we just don't really pay attention to it. But here's oxygen. Oxygen has a 16. It also has a 17. So this is an M+1. But look, it's squat. 0.04%. Who cares? Well, oxygen also has 18. This is an M+2 peak. 0.2%. Well, it's lower than the nitrogen. And I told you that we didn't worry about the nitrogen, but the reason we worry about oxygen is because it is more common. If I'm going to see functional groups, think about it. We saw them in infrared. My carbon double bond O, my carbon double bond OH, my carbon double bond with another double bond O, my carbon double bond O in between a molecule, esters, anhydrides, amides, ketones, aldehydes, all of them, alcohols, carboxylic acids, they all had oxygen. That is why we say we have to worry about this one, because oxygen is running rampant. It's everywhere in a molecule. And because of that, we have more choices, we have more chances of it showing an M+2 peak when it's present. Nitrogen, not so much. Yeah, they're going to be involved in an organic. They're going to show up. It does have an M+1 peak. It's just not as common as an oxygen, though. Sorry. Look at my sulfur. Sulfur 32 to sulfur 33. This is an M+1 peak. I don't really contribute that to M+1, though, because sulfur, again, is very rare. Yes, we do have it in organic. Yes, we will see it. But sulfur, not so much. Okay? Well, I also have a sulfur 34. Whoa. 32 to 34, that's an M+2 peak. Whoa, 4.22%. So if sulfur is present, I'm going to see it. That M+2 peak is going to be a little bit taller than normal because the percentage of it is much higher. And then sulfur 36, if it starts out to be 32, this is an M+4 peak. But look at this guy, 0.02%. Give me a break. I probably never will even see it on the spectrum. If I zoom in real close, I'll see it. But just at a normal glance, no big deal again. Fluorine's pretty easy. Fluorine, 19. That's it. Fluorine is part of Weight Watchers. It controls its weight all the time, and typically close to 100%, it's going to be fluorine 19. There is no M plus 1. There is no M plus 2. There is no M plus 3 or M plus 4. Chlorine. Chlorine at 35 and chlorine at 37. Well, this is an M plus 2. 75 to 24%. What does that mean for us? And look at bromine. Bromine 79 and bromine 81. This is also a M plus 2 peak. But gosh, look at the percentage. It's almost 50-50. And iodine is like fluorine. Weight Watchers doesn't really change its weight that much. Close to 100% of I-127. No M plus 1, M plus 2, M plus 3s, M plus 4s, no nothing. So we said that M plus 2 exists. It is typically due to oxygen because oxygen is the most common that we always see. It's going to be involved in most of the compounds if it's not a hydrocarbon. That's just kind of common. But these two also contribute to an M plus 2. And more than that, they contribute even more. 25%, all the way to 50%. What does that mean to me? Why should that even matter? On a mass spectrum, if I see an M peak that's going to be right here, let's say that this is the M peak. If I see something that's very tiny, this is, if it's an M plus 2, this is typically due to the oxygen that's present. However, at that M plus 2 peak, if this goes about a third of the way up, a third of the height, this is a very good sign that chlorine is present in the molecule. I've just identified a weird little atom that doesn't show up most of the time, but if that M plus 2 peak's present, and it's about 1/3 of the abundance of the M peak, that's a good sign that chlorine's there. And then, if it goes and matches the height, this is a very good sign that bromine is present. Because think about it, this was a 50-50 split. All right? So by looking at the M plus 2, I will be able to quickly determine if this compound is halogenated. Specifically with bromine or chlorine, which is the most common halogen that we put on an organic. We don't really see iodine. He's too fat, too large. We don't really see fluorine because he's so temperamental and too reactive. If we do see halogenated compounds, they're typically going to be bromine or chlorine that's going to be present. And this is a way that I can quickly determine if the molecule that we shot into the mass spectrometer is a halogen or not. Look at the M plus 2 peak. How high is it? If it's super tiny, then no, they're not there. If it's about 1/3 of the height, then yes, chlorine is going to be present. And if it matches the height, it's a very good sign that bromine is attached to the molecule. So just some more tidbits of information that I can pull from the spectrum if I do not have a database, or if my database is not working, or if I'm given a mass spectra and I'm told to analyze it from scratch. These are the things that we should be taking away from that information. All right? So keep in mind, these are the most common groups that we typically see. Chlorine and bromine have the highest percentage of isotopes that are basically on this list, which is why they're so dominant in the spectrum. And oxygen, pretty common in a molecule, and this is where typically my M plus 2s will always come from. Yes, sure, There's other N+2s that are here, like the sulfur. However, these are not as common to be found on a molecule. So that's where I'm stopping this video. We're going to go on and talk about another typical calculation that I can pull from this information that will give me some more ideas of how this molecule is structured and what's making it up.